Welcome! Today I'm going to be talking about compilers, how they work, and how we can build one from scratch. Throughout this process, we'll get some answers to some really interesting questions. First, how do our computers actually compute? Second, how do programming languages work on the inside? Third, how can we create our own programming languages? And finally, how can we design elegant compilers? Today, I'm going to tackle these questions by examining a couple of virtual machines, along with an in-depth exploration of a compiler I've written over the past few years. Hi, I'm Adam. Nice to meet you. I'm a 22-year-old PhD student at the University of Tennessee. I just finished my master's degree. I started experimenting with my own compilers when I was in high school, and I've been in love with the subject ever since. I write all kinds of software though, like shells, text editors, chess engines, operating systems, cryptography libraries, and more. Check out my website if you want to know more about my endeavors. So, what's a compiler? Simply put, a compiler is a program that transforms source code into machine code. Inside a compiler, we have a few components: the parser, an intermediate representation, and a code generator. The exact problem a compiler solves and the components that constitute a compiler seem pretty complicated, the kind of stuff a wizard in his ivory tower works on. Let me simplify it for you with an analogy. Programmers set out to write a program by starting with some code that's designed for a person to understand. This is called source code. Source code has many features that make it comfortable for humans to work with. Humans think in very abstract terms, and source code allows us to articulate our commands to the computer in a form that resembles these abstractions. You can think about programs written in source code as novels written in modern English. English has a massive vocabulary and bank of idioms to draw from to express our thoughts simply. The computer, however, is like a very, very primitive caveman who only understands grunts and gestures. Even worse, there are very few grunts and gestures that the caveman has memorized with his caveman brain, so we need to work really hard to translate our novel into a language that the caveman can understand. This is where the compiler comes in. The compiler is a program that takes our source code and translates it into a form that the computer can understand. This form is called machine code. Machine code is a series of binary instructions that the computer can execute directly. It's the grunts and gestures that the caveman knows how to speak. But the compiler doesn't just translate source code directly into the grunts and gestures. That's a monumental task that would be incredibly difficult to get right. Instead, the compiler translates source code into an intermediate language that's easier to work with. So, for example, the compiler might translate our English novel into Ancient Sumerian, which has a much smaller vocabulary and grammar rules that are easier to understand. Translating Ancient Sumerian into grunts and gestures is simpler than translating English directly. Conveniently, it's also easier to translate English into Ancient Sumerian than to the grunts and gestures. In a compiler, we might go through various stages of translations, each one getting us closer to the grunts and gestures that the computer can understand. So now that we have an overview of what a compiler is, let's first delve into a sample language that we might translate a novel into. Our first caveman's brain only has two lobes: a lobe for containing a list of numbers, and a lobe that's thinking about only one of those numbers in the list at a time. These numbers can only be from 0 to 255, so incrementing a number at 255 makes it wrap to 0, and decrementing a number at 0 makes it wrap to 255. Our caveman can only understand 8 utterances that tell him what to do. A plus sign tells him to increment the current number he's thinking about, and a minus sign tells him to decrement the current number. A left angle bracket tells him to think about the next number to the left, and a right angle bracket tells him to do the same for the right. A dot tells him to say the current number he's thinking about aloud. A comma tells him to replace the number he's thinking about with the next number that you say. A left square bracket tells him to enter a loop of commands while the number he's thinking about is not 0. And finally, a right square bracket marks the end of that loop. So, let's see what our caveman does with an initial brain state and some commands. Wow, how cool. He was able to add together the first two numbers in the list and then tell us hi. What a friendly caveman. Despite the tiny size of his brain, the caveman we just spoke with can perform any computable task. He's Turing complete. If you want, he could even pilot your rocket ship to the moon. Although there are a few reasons why you wouldn't want this particular caveman in the driver's seat. The time complexity for almost everything is god-awful, Adding two numbers together takes longer the larger the numbers are, even though the numbers are just bytes. We can add 64-bit numbers in a single operation on modern computers. Also, there's no way to represent functions, so we can't divide our code into useful subroutines that our caveman can reuse. Finally, there's no built-in way for our caveman to run commands that aren't his. We want our caveman to be able to dispatch instructions to expert friends that specialize in whittling or rock carving. Enter our next caveman. This caveman has a few more lobes in his brain that will help address the drawbacks of the last one we spoke with. He has some extra memory to work with and can jump around in his list of numbers in a much more intelligent way. Additionally, he's able to reuse his own instructions and dispatch instructions to other cavemen. Even better, the caveman can perform multiple operations simultaneously on a smaller list of numbers, which makes him a lot faster in certain situations. This is the caveman we'll spend the rest of the video trying to talk to. He's quite charming. The name of this particular caveman I've created is the Sage Virtual Machine. It describes a model of computation that's based on the last model that we discussed. It's a loose superset. It's Turing tape based like the last caveman. It only adds a few more lobes to his brain and a few more utterances. This is all for a great payoff though. This caveman will allow us to write programs that express really high-level concepts, such as generic algebraic data types, pattern matching, polymorphic functions, and more. It's enough to support real software in a straightforward way. I've implemented a shell, a PowerPoint app, and AES encryption plus decryption on top of this virtual machine. This model allows us to write portable, efficient code that runs well on real machines. Now let's take a quick look at the new components of the caveman's brain. First, our caveman's memory has been upgraded to store entire 64-bit numbers instead of just 8-bit numbers. This allows our caveman to perform math operations on a much larger scale with ease. Second, our caveman now has a smaller list of cells called the register, or accumulator. It functions as the caveman's short-term memory, allowing him to hold these temporary values while he's working on a larger problem. Third, we add a lobe to his brain for bookkeeping his movements around the main list of numbers. It allows him to quickly leap around the tape without losing his place. Finally, we add some bookkeeping for function calls, so the caveman doesn't forget where he was when he jumps to a new subroutine. The Sage VM adds some new instructions to the caveman's vocabulary and modifies some existing ones. I'll cover the core ones here. The set instruction allows us to directly set the register cells to some constant values. The move instruction functions a lot like the angle brackets from the last machine. We can move the pointer into the main list of numbers to the left or right by some number of cells. The load and store instructions allow us to read values from memory into the register or write from the register into memory. The deref and refer instructions enhance the caveman's ability to move around the tape. Deref treats the value in the current main memory cell as the new pointer and leaps to that position. Refer does the opposite, undoing the last deref operation. Where, offset, and index allow us to manipulate pointer values in a way that avoids requiring the knowledge of how the caveman is representing the pointer in his head. This way we can interface with existing pointer functions from other cavemen, like malloc and free. We also add some element-wise arithmetic instructions to the caveman's vocabulary. These modify the register values according to the main memory contents. The add, subtract, multiply, and divide instructions allow us to perform simple arithmetic operations on the register values with the main memory cells. The main memory values are left unchanged. The negate instruction negates the values in the register cells. The is non-negative instruction sets each value in the register to 1 if the value is non-negative and 0 otherwise. Finally, we add some control flow instructions to the caveman's vocabulary. The function instruction marks the beginning of a new subroutine. The call instruction jumps to a subroutine. If the first register value is 0, the caveman jumps to the first defined subroutine. If the first register value is 1, the caveman jumps to the second defined subroutine, and so on. The return instruction jumps back to the last place the caveman was before he jumped to the current subroutine. The while instruction functions identically to the left square bracket from the last machine, allowing the caveman to loop over a block of code while the register values are non-zero. The if and else instructions allow the caveman to make one-time decisions about which block of code to execute. And finally, the end instruction marks the end of a block of code. Some of the other instructions are omitted for brevity. This includes instructions for bitwise arithmetic, Boolean logic, along with some floating point instructions, which have nearly identical functionality to the integer instructions. Now let's see our caveman do some work. Wow, this caveman is greeting complete too. That simple program is also a lot easier to comprehend than the last one we saw. Great, now we have something tangible to translate our novels to. All that's left is to write a translator that takes our source code and translates it into Sage virtual machine code. If we want to run our VM code on a real machine though, we'll have to perform another translation step. We can treat Sage VM code as another source language, and then write a compiler that translates it into machine code. That's very simple, however, because the Sage VM doesn't have all the abstraction that makes translation difficult. Let's look at an example of how we might translate some Sage VM code into a real computer's machine code, the x86-64 instruction set. Here we see two equivalent programs, one in Sage VM code and one in x86-64 assembly. The x86-64 assembly is a bit more verbose, but it's still pretty easy to understand. For each Sage instruction, there are only 3 to 5 corresponding x86-64 instructions. That's not too bad. As we discussed previously, it's difficult to translate source code directly into a low-level target language. Instead, we translate to an intermediate language before even compiling to Sage VM code. This intermediate language is called Sage Assembly, or Sage IR, short for Sage Intermediate Representation. First, our parser reads in the source code. Then we go through some translation steps to lower to Sage IR and then to Sage VM code. Finally, we can lower Sage VM code to our desired target language, such as x86-64 assembly. So, without further ado, let's talk about the IR. The IR is still very simple, but it adds a cave full of features that make it easier for us modern humans to speak. This way, we'll have a much easier time translating our source code to it. The IR adds tons of new features on top of our virtual machine. Now we have access to global variables that we can use throughout the entire program. Allocating the memory on the tape is done for us by the IR. We also have access to a stack for pushing and popping our function arguments and local variables. Additionally, we have a frame pointer that helps us manage our stack frames for the functions we define. This way, it's simple to add local variables for each scope and simply tear them down when we're done with them. The IR provides some general purpose registers for temporary space without having the additional overhead of manipulating the stack. We also get access to named functions and an interface for calling foreign functions. Finally, there are tons of new IR instructions that make it easy for us to translate certain address operations into the Sage VM's more primitive instructions. Now we can use instructions like let effective address to easily calculate the address of our local variables. Now let's see an example of how our IR gets transformed into Sage VM code. As you can see, the resulting code is pretty obfuscated. It's not straightforward to see what's going on. This tells us that the IR is doing a lot of work for us. Another interesting property is that it's really hard to reverse engineer what our code is doing, making this a great platform for writing obfuscated machine code. Our new abstractions are represented by mapping user-available and internal registers at special locations on the tape. Whenever we perform stack instructions or access global variables, we're actually secretly manipulating the tape in a manner that's abstracted away from us. Now that we finally have something that's straightforward to map a high-level language to, we can start compiling some source code. Let's take a look at some sample front-end code written in the Sage source language. Wow, that's some abstract code. Here we show a program that implements a simple nullable type named option with an unwrap method that throws an error if the value is nothing, or else retrieves the value inside. We use this in our main function to define an option that contains a number 5, and then unwrap it and print the value. On the right, we can see the corresponding Sage IR that's generated for the program. It's more verbose than our input program, but it's so much easier to understand than the Sage VM code. We can see how our functions instantiate our variables on the stack by pushing them, and how it performs our unwrap and print operations by doing the appropriate if statements and IO operations. Now let's examine the compilation process for some example programs. First, let's look at a simple variable declaration. Here we declare a function test that just declares a variable x as 5 and prints out its value. In our program scope, we call the test function to ensure that its contents get compiled and executed. On the right, we see our function name got mangled by the compiler, but there's only one function in our program, so it's easy to identify. First, we see that the compiler uses a pushConst instruction to push the constant literal 5 onto the stack, instantiating our variable x in the function stack frame. Then it pushes our value onto the stack and prints out the value there. Finally, it tears down the stack frame and exits the function. In the main scope, we can see the compiler calls our test function by storing its function pointer in the register A, and then calls the function pointer stored there. Next, let's look at how structures are compiled and represented in the IR. Here we define a structure position that contains two integer fields, x and y. Next, we declare a structure vector, which contains two position fields, start and end. The resulting IR code is even shorter than our original input program. On the stack, the compiler allocates each field in alphabetical order and stores each value consecutively in memory without padding or alignment. Our two positions are pushed onto the stack together, the first one containing x equals 5 and y equals 6, and the second containing x equals 1 and y equals 2. Then, to create our vector v, the compiler pushes the two positions on the stack, first the end position and then the start position. The end is stored before the start because the fields are pushed in alphabetical order. Finally, the compiler tears down the scope and exits the program. Finally, let's look at how some types are compiled and represented in the IR. Here we define a generic linked list type called list, which can either be nil or cons. A cons value contains a pointer to the next list element and a value of type t. The nil value is a list element that represents the end of the list. We declare a list of integers that's 3 elements long, containing the elements 1, 2, and 3. The resulting IR code is longer than the previous examples, but it's still easy to understand. First, the compiler allocates space for our first variable, end of list. This variable is a nil list value. The size of each list value is 3 cells, because the largest subtype cons requires 2 cells for its field, and we store the tag in the last cell at the end. The compiler allocates 3 cells for the nil value, and stores the tag 1 in the last cell. Tags are also sorted in alphabetical order, so cons will have a tag of 0. Then, we repeatedly allocate 3 more list values on the stack, each of size 3 and a tag of 0 for cons. Each time we allocate another list node, we calculate the address of the previous node and store it in the next field of the new node. Finally, the compiler tears down the stack and exits the program. Although we've talked about using polymorphic values in the language, we haven't yet discussed how the compiler handles polymorphic code. Polymorphic code is code that can be used with multiple generic types. Whenever we instantiate polymorphic code for a given type, the compiler has to compile that code for the specific type. Whenever we use that code again with a different type, the compiler has to recompile it for the new type, storing multiple copies of the function. This process is called monomorphization, and each copy of the function is called a monomorph. This was one of the hardest parts of the compiler to get right, but it's an essential feature for a high-level language. Here's an example of 2 copies of the same function, each compiled for different generic types. The code is too complex to explain in detail, but you can see there are various small changes between the 2 copies, namely the differences in the sizes of values passed around. On the left, we see a monomorph that was compiled for the type int, and on the right, we see a monomorph that was compiled for a tuple of 2 integers. In the tuple monomorph, we see that the compiler uses more space on the stack to store the tuple compared to the monomorph on the left, just using 1 integer. Although these functions are nearly identical, they have irreconcilable differences in how they use their data, so they must be managed separately. Using the wrong monomorph will cause your program to crash or produce incorrect results. Although compilation itself is a really hard problem, implementing a sound type checker can be even harder depending on the type system. Verifying that code itself is correct instead of just translating the incorrect code as it's written is an immense challenge, but it's essential for producing a language that's usable by developers. Oftentimes, the hardest part about writing a type checker is decidability. The type system and the type checker must be designed such that the compiler can determine whether a program is well typed in a finite amount of time. No infinite loops allowed. The type checker must always halt. Without this property, the compiler could hang indefinitely, or worse, crash. This prevents the user from being able to extract any information about an error in their code. Now let's discuss how the Sage type checker is architected. Sage divides code into 3 categories: expressions, constants, and types. Constants are a subset of expressions. Every constant is a valid expression. Types are also a subset of constants. Every type is a valid constant. In every expression, the compiler infers what the expected type should be from the context in which it's used. This is called type inference. Whenever a type is inferred by the expression it's used in, the compiler checks that the inferred type matches the expected type in other expressions. To perform these comparisons, the compiler performs structural equality checks on the types. This means that the compiler checks that the types are identical in structure, not just that they have the same name. Two types with different names but the same structure are considered equal. Now that we've written our compiler and type checker, we can start writing some real programs. Let's see what we can do with our new language. First, a demonstration of a couple of real-world programs written in Sage. Here we see an operating system with its entire user space written in Sage. The operating system boots to a shell implemented using the Sage source language and compiled for the RISC-V architecture. We use the shell to boot up another Sage program, a PowerPoint app which delivers a presentation about the operating system's structure and implementation. Then the PowerPoint finishes, and we return to the shell to run some more commands and navigate the file system. Because the Sage VM is so simple, it's really easy to get it working in the web. Here, I've set up a Sage compiler and VM that runs entirely in the browser, hosted statically on GitHub pages. Using the web interface, you can see the various stages of compilation and execute the compiled code. The compiler also uses a VM backend with JavaScript interop, so you can call supported JavaScript functions like eval from your Sage code. I've prepared a few examples in the web demo. First, we have a simple hello world, then a factorial program. Next, a hash map implementation written from scratch. Additionally, we have a couple of examples that use the JavaScript interop to create a canvas on the page and draw some neat shapes. Finally, I show an implementation of AES encryption and decryption compiling and executing in the browser. We've covered a lot of ground in this video. We discussed some example virtual machines and the process of compiling our source code to a given virtual machine. Additionally, we talked about the translation of virtual machine code to real machine code. We also talked about some of the difficulties of performing the various compilation stages, the unwieldiness of translating polymorphic code, the pitfalls of type checking, and creating intermediate representations that are easy to work with. Now, let's recap our questions from the beginning of the video. First, how do our computers actually compute? Second, how do programming languages work on the inside? Third, how can we create our own programming languages? And finally, how can we design elegant compilers? Our computers perform computation by providing a small set of building block instructions called machine code that we can compose together to express our thoughts. Programming languages work by translating our high-level source code into a form that the computer can understand. This translation process is done in multiple stages, with each stage getting us closer to the machine code. We can create our own programming languages by creating a compiler with a parser, IR, and a code generator. The compiler translates our source code into machine code, allowing us to execute the programs in our new language. Finally, we can design elegant compilers by performing small, incremental transformations on the input code at each stage of the compilation process, making simple translations from one representation to another. This way, it's easier to reason about how our code is transformed to the end result. Thank you so much for watching. I hope you enjoyed this video as much as I enjoyed making it. If you liked this video, you might enjoy some of my other content on my blog. I write about all kinds of programming topics, but mostly compilers, I must admit. It's been a pleasure sharing my work on compilers with you. I'll see you soon. Adios!